All right, hello, good morning, afternoon, or evening, or whenever you are viewing this video. So it is currently Sunday night as of time of recording. You will be having this test on Friday, and I will be posting this study guide review video Monday after school. I'm going to be doing something a little bit differently with the practice problems. I'm going to post the practice problems, but I'm not going to post the answers. And my accompanying video until Wednesday night. The goal of that is to kind of get you to start studying for this material Monday and Tuesday night rather than, you know, starting with just the answers and all that stuff. So, what this video is going to be is going through the test study guide and just really explaining stuff. This is not going to be practice problems. This is kind of just like a narrated lecture. Um, in that sense. I guess what's nice about it is if you zone out in class, which I get it, that happens. Lectures can be tough to swallow. This still gives you the opportunity to kind of get me going through stuff. Um, I will, you can stop this and pause it and come back to it. It kind of gives you that flexibility. Without further ado, let's get back into this. Oh, before I actually get into this, I just want to say that I'm going to discuss anything that is for the honors class and for their tests specifically at the end. That way, if you're watching this from scholars, you don't have to, skip through certain parts. So I'll let you know when that time comes. All right, now we can actually get started. First section right here. This is stuff from the Quiz Plus that's going to be on this test. Um, I'm basically kind of assuming that a lot of the basic stuff from that Quiz Plus, you know. I decided to split it up into two parts, really just to not overload this quiz, excuse me, to overload this test too much. But you should know what this notation means. 235U. You need to know that. The nomenclature stuff, the atomic symbols, the protons, all that stuff. That's kind of the biggest takeaway. Um, We're not going to be talking too much about charge just yet. I still wanted to introduce that in the first part because we're going to be talking about charge very soon. Trust me. Um, but for now, you need to know what this means. U235. Um, just resumming or summing up, this number in the top left, this is the mass number. This basically tells you protons plus the neutrons in the nucleus. So if you look up nucleus of an atom, right? So it's the stuff in the middle. It is all the protons and the neutrons. All this stuff. So these are protons. Can't see the red on the red. And the neutrons. That's basically what is in the nucleus. We're caring about the nucleus for nuclear chemistry. That's where that gets the name from. Nuclear chemistry deals with the nucleus. The rest of this course, we care about the electrons. But for right now, for nuclear chemistry, we care about the nucleus. You should know, and this is again something that we had previously gone over, you should know what the atomic number means on the periodic table. You should know what that represents. Uranium, 92. And you'll see the notation like this when we get to equations later. I mean, I can just scroll down through all this stuff now. This notation here, you should know what that 92 means, the 2 means, and the 90 means. That tells you how many protons are in that atom. There are a few examples, but such as the beta particle, but we'll get to that. 92, uranium. And the way you get that, do your periodic table. The number in the top left, right here, is the atomic number. That is how many protons there are in that atom. You gotta know that. Gotta know that. This number right here is the atomic mass. We're going to get to that in a bit, but you have to know titanium always has 22 protons. If you add one more proton and you have 23, then you get to vanadium. The amount of protons is this atomic number. So we go to uranium all the way down here, 92. Uranium will always have 92 protons. That's what makes it uranium. Doesn't matter the neutrons, doesn't matter the electrons, 92 protons makes uranium. Gotta know that. Isotopes and atomic mass. So we are talking a lot about different isotopes, radioactive isotopes. Some isotopes are radioactive, some are not. Isotopes are the same element, which means they have the same amount of protons, but their mass is different because they have a different amount of neutrons. If we look up, let's see here, isotopes of carbon. We got a nice, here we go, nice little image here. Carbon, we should really say this is carbon 12. Carbon 12, 6 protons, 6 neutrons. 6 plus 6 equals 12. Carbon 13, they all have 6 protons, but their neutrons are different. 6 neutrons, 7 neutrons, 8 neutrons. That increases the mass. Carbon 12 has a mass of 12. Carbon 13 has a mass of 13. Carbon 14 has a mass of 14 because you're adding one more neutron every time. This changes the mass. These are 3 different isotopes. So you have 12 carbon, 13 carbon, and 14 carbon, or carbon 14. These are the 3 different isotopes of carbon. So you gotta know that. Alright. Alright. If there's a break, I accidentally hit the pause button. Thumbs up. I realize I can do this. Gotta know that. Isotopes have a different mass. The atomic mass. Go back to your periodic table. What you see here, 238.03. That is the average mass of all of the different isotopes combined. However, for example, carbon is just a little bit over 12. We go back to our isotopes of carbon. There's carbon 12, 13, and 14. So why is that number not smack in the middle? Because there are different percentages of carbon. If we look at this image here, this is the relative abundance. What percentage of carbon atoms are carbon 12? About 98.9%. About 1.1% are carbon 13, and this amount, less than 0.0001% of carbon atoms, are carbon 14. Alright, so what does that mean? That means that when we get our average mass, we go back here, it is a weighted average. You take the mass of the isotope 1, multiply it by the percentage of isotope 1. That percentage must be in a decimal form. So if we're going to go back to carbon, I'm going to load this image up. Right? So if we were to, we're going to ignore carbon 14 because its percentage is so low. I wouldn't give you something like that's low. So we're just gonna shoop. So what our calculation would be, we have carbon 12. We're gonna say it has a mass of 12, which it actually does. So the atomic mass, this is this weighted average, equals 12, which is the mass of carbon 12, times 98.9% in a decimal form. To get that, you take 98.9 divided by 100. This gives you your decimal place. 0.989 plus, I'm going to just put it down below, we have a mass of 13 times 1.1 over 100, which would give us 0.011. And if we put this into a calculator, oh no, why is my thing in? My calculator is in scientific. Okay, there we go. 12 times 0.989 plus. Oh, yeah, this calculator doesn't give me. Okay, whatever I did, it's working now, I think. Alright, I'm gonna pause and I'm gonna come back once I figure this one out. Alright, whatever I did, I got it to fix, so welcome back. And then I'm going to, so I did 12 times 0.989 times 13 plus 0.011. Oh, I did a plus instead of add. Oh, I figured it out. I'm pressing X instead of for multiply. Alright, so we're doing 13 times 0.011 plus 11.868. This gives us 12.011. And if we go to our periodic table, that matches 12.011. That's how you would get that. That is kind of the link. All right, so you're going to see a question. It's going to look like this. Get rid of this stuff. Don't need this. All right, you're going to be, you might have one that has more than one isotope. Instead of, you just add another, whatever that isotope is, times that percentage of that isotope. We're going to go over this in class on our review day. Notice that the percentage is always going to add up to 100. So it was 98.9 plus 1.1. They add up to 100%. You're going to need to know how to calculate the atomic mass of an element given the atomic mass. This is that whole x1 minus x deal. You can look for practice problems with that one. I'm not going to go through that just here. I'm going to go through that on the practice problems video. All right. Nuclear chemistry, just things in general. What to know. First, nuclear reactions change the amount of protons in an atom. So this is when you are changing the element. So there's a whole branch of medieval science known as alchemy, when the whole purpose was to change lead into gold. Now, with the methods that they used back then, that was not possible. But turning lead, which is elements, if we go to our periodic table, 82 into gold, which is element 79, by all technicalities is possible with nuclear chemistry by changing the amount of protons. It's not efficient. You would lose a lot of money doing it. You probably would get a very low amount of gold, but technically I believe it's possible. That's kind of what nuclear chemistry does, is it changes the elements. All of these elements down here, they were created by basically smushing two smaller atoms together to create this one bigger atom. That's how they made these atoms. They said, all right, this atom has 110 protons, so let's take something that's got half of that, or 2/3 of that, and something that's got 1/3 of it, and smush them together, and you made this element. Second, nuclear reactions release a ton of energy. The amount of energy inside the nucleus that's smushing those protons and neutrons together is magnitudes more than the electrons and the chemical bonds that we're going to be seeing in future chapters. Just know this is why the amount of fuel for a nuclear reactor is about this much for barrels and barrels of energy-rich oil. So the nucleus is held together a lot more energetically than anything else that we're going to see. The numbers may not make much sense when you see, oh, this is this amount of joules, but just trust me, nuclear reactions have a ton of energy involved per reaction compared to chemical reactions. Radioactivity. This comes from an unstable nucleus. The nuclei, to the plural nucleus, they're in this tug of war battle. One side is the proton-proton repulsion. Proton repulsion. About to say that 20 times fast. Here we go. It's kind of the image looking at it, right? On one side, you have the electric repulsion. These protons. Oh, it's not letting me. These protons right here are trying to push each other apart. But this strong nuclear force is kind of this glue that sticks it together. So you have these two forces fighting off against each other. In a stable atom, they're about equal. But in an unstable atom, they are one side is winning. And radioactive decay is the atom's attempt to rectify that, to become stable. When one side is winning, you might have too many protons or too many neutrons. That's what causes a radioactive atom to occur. I will get back to this for honors. Radioactive decay. This is the process by which an unstable nucleus becomes stable. Big important to note that this happens naturally. Radioactive atoms on their own are so unstable that they will just do this spontaneously. You don't need to do anything. You don't need to poke this atom for it to decay. It will do it on its own. First type of decay, we have alpha decay. I want to visualize this. Not example. Basically, alpha decay happens when you have this super big particle. It's probably a better picture of it. Big, yeah, big nucleus, unstable, too many protons. We talked about this for honors, why kind of the distance of these forces are different. This is unstable, and it's going to shed 2 protons and 2 neutrons. Smaller, but more stable nucleus. That's the purpose of this, is for stability. And you get this alpha particle. This is a helium nucleus with no electrons, so it is a +2 charged helium. It is important to note, if we get back to my notes here, this lowers the proton-proton repulsion and makes it more stable. It is emitted at a high speed, which means it has a lot of energy. That's where that whole energy comes from, right? This energy being released, part of that energy being released is the kinetic energy. That is a type of energy. So, alpha particles, really big nuclei that want to get rid of some protons. Beta decay, too many neutrons. Too many neutrons, one of those neutrons turns into a proton and an electron. Not going to get into why or how that happens. But that's basically just what it does. It turns into an electron. This neutron turns into an electron and a proton, and then ejects that electron super fast. So this is not one of those electrons that are circling the rest of the atom. This is from the nucleus, and it throws away that electron. That electron becomes known as a beta particle. This big ball of, it's not really that big, it's actually really small, but it's a small ball of hurtling electron negative charge. Lastly, gamma decay. If you have too much stored energy, sometimes the energy is released, or most of the time is released as the kinetic energy, but sometimes that energy stays inside the nucleus. It's kind of like a residual just left over, and there's too much. So you have this gamma ray that is released from this it has too much energy, it's unstable, and it kind of kamehameha just releases all that energy off in a beam known as a gamma ray. We're going to get into light probably in the next chapter, so just know that it is pure energy, and it is a very high amount of energy. But it is light moving so it moves at the speed of light. Okay? And we're going to get to this tomorrow for scholars as well. The difference in these reactions releasing energy is due to a difference in mass. between the initial atom and the resulting more stable atoms. So some of that mass is lost. In reality, that mass is actually converted to energy. That's where that kinetic energy comes from. It is converted into energy using Einstein's famous formula, equals mc squared. And I'll say this now, honors, you're going to be calculating this amount. So you should be knowing how to do that on the calculator. Radioactive decay and half-lives. This process that I've just discussed can either take billions of years for it to occur if you have a relatively stable radioactive isotope. Maybe it's a very close tug of war and it's just a little bit of an advantage to one side, or it can take fractions of a second. Maybe you have the entire, football team on one side and you have a cat on the other side. Then it's going to be a very quick game of tug of war. It is, however, impossible to say when a certain individual atom will decay. If you were to watch through a lens one atom that of uranium or any other radioactive isotope, you can never say for certain when that specific atom would decay. Instead, you have to follow the pattern of all of the atoms. A certain amount, if you have a sample that has millions and billions of atoms worth of a radioactive isotope, then you can tell some general trends. You can tell how long it will take for a sample for half of it to decay. This is known as the half-life. So, if you have a radioactive isotope, say you have 10 grams of carbon-14, after its half-life, which is 5,730 years, you will have half the amount, or 5 grams will be left. You don't know which specific of those grams or of those atoms will decay, but you know overall how much you will have. And this time is unique. This half-life is unique to each individual radioactive isotope. Basically, the more stable it is overall, the longer this half-life is going to be. For scholars, you need to answer simple calculations about a radioactive sample. These are kind of like the questions that are on the lab, which you'll be handing in before Thanksgiving. For example, how much of a sample is left after 3 half-lives? How many years would it take for there to be 25% of a sample left? So on and so forth. If you have 3 half-lives, just as an example, you start with 100 grams. After 1 half-life, you'd have 50 grams. Half of it's gone. After another half-life, you would have 25 grams. And after a third half-life, you would have 12.5 grams. How many years would it take for there to be 25% of a sample left? So that depends on the half-life. So 25%, I mean, these are already in 100. That would be 2 half-lives. So if the half-life was, let's just say, 50 years, it would take 2 times 50 would take 100 years. You also are going to need to read a graph that gives these estimates at specific times. This is, again, kind of the lab question. Let me get back here. A half-life graph. Right, so something that looks like this. Well, I want one that's a little bit more specific. These graphs kind of suck. I might make one just as a kind of rule. Well, this is the one that I used on. This is the one that I used on your lab, so I'll just use it here. Right here, if we were at, let's say, 1.5 half-lives, and I said 10 years, I wouldn't have you do this, but if it was 10 years, right, which is about, let's just say, 10 years is a little bit less than 2 half-lives, so about where I'm joining my mouse right now, you would estimate that you would have about this much, so you would say maybe Let's just say 2.8 grams after 10 years. This is an estimate. You're reading the graph. As long as it's relatively close, you'd get credit. If you said, 1 gram, and that's, all the way over here, that's not right. If you say 2.75, you said even 3. Basically, if you didn't say 2.5, anywhere from like 2.6 to about 3, somewhere between that, or 3.5 probably, you would get, credit. It's an estimation. All right. All right. Honors, I will get back to this. Nuclear equations. You need to calculate nuclear equations for a missing variable. So if I did not have this right here, you would need to say, okay, well, then what is this? So basically, the top and the bottom are the same. They must be the same amount. So 235. Oh, I didn't mean to do that. So 235 equals x plus 231. Here is the top, and here is the bottom. You have 92 equals x plus 90. This is pretty simple algebra here. All right. You get your top, x would equal 4. The bottom would equal 2. So you'd have 4, 2. And then you're going to need to look up. You're going to need to know. I have the bottom number here is protons. Go to your periodic table. Here is number 2. So that is helium. All right. You're going to need to have to do that. So this is one of those things I talked about in the very beginning of this video. I'm not gonna have you memorize what alpha or beta particles are, like their mass. But you should know that a beta particle has a -1 proton count for math reasons. So an example of this, if you take carbon 14, this will decay with a beta decay into nitrogen. I'm going to use the beta symbol here. So basically for math reasons, that's the way to think about it. One of these neutrons, carbon 14 has 8 neutrons, turns into a proton. So the mass numbers here stays the same. An electron, we say it doesn't have a mass number. That's the assumption it doesn't have a mass, even though it's just very, very small. One of these protons from carbon 14 one of the neutrons turns into a proton. So we start with 6 protons in carbon, and because one of those neutrons turns into a proton, we now have 7. So this -1 right here is really just making this math look good. If an electron doesn't have a -1 protons, it's really just makes our math look good. 6 equals 7 plus -1. There's your math. Makes it nice and simple. 6 equals 6. Just wanted to say that. All right, you're gonna need to adapt whatever I throw to you at you. I have some ideas of what I might do with this. We'll see. You're gonna have to do a few of these. That's all I'm gonna say. You should do it. You're gonna need to be able to do at least, we'll say, 4 of these at a minimum. Radioactive decay safety. You should know the whole penetrating power and the ionization power. What this is. Why are alpha particles so dangerous inside the body? Yet why are they also stopped by a piece of paper? So just quickly, penetrating power. How much the particle can go through. Um, we can look at. I'm gonna nuclear or radioactive a penetrating power. Right, this kind of stuff. That's a that's a really bad image. That's really small. Okay, here we go. We're not talking about neutron beams, but the top 3 here. Got to know what this is. Alpha particles are the largest, so they are bulkier. They can't go through stuff as much. Beta particles are a little bit smaller, so they can get through some stuff. But the alpha or the gamma rays, you need something thick, like lead or iron, to stop it. So it all depends on how big the thing is and how much speed it has. However, because alpha particles have the most charge, they are like vacuums for electrons inside your body. They're going to steal the electrons and turn them into an ion of things that are important, like your DNA, which is how radiation will kill you. So, not very fun. Beta particles are kind of in the middle, and gamma rays can still hurt you because they can penetrate you. Even if their ionization power is low, they're still going to do damage, and they're going to kill you, like Bruce Banner. Alright, nuclear fusion and fission. I'd love to have gotten more about this, but, you know, I did have to kind of rush a little bit through this chapter. Nuclear fission. Let me say that 10 times fast. Fission is splitting up of large atoms. Oh, fissure, breaking something in half. Um, Basically, if something is broken in half, it is fissured. If you're seeing the cut of this, I googled fissure and did not get the results that I wanted. So I had to make a cut in this video. So, nuclear fissure. Nuclear fission. Excuse me. It is you take something, this is man-made, you throw it at a big atom, breaks in two, releases a ton of energy. That's what you got right here. This neutron thrown at the nucleus here. Destroys this nucleus, splits it up into two pieces, releases a ton of energy. It also releases three more neutrons, which then can complete the cycle. These three neutrons can bump into more uranium and explode it and have more energy and release even more neutrons. That is the chain reaction that creates nuclear bombs. All right, that's what happens. They continue to split, they continue to destroy them, and it's kind of just it adds up really, really fast, and it goes boom. However, nuclear fission can be used to generate electricity. You basically can control the amount of neutrons that are released. These are called control rods. So you don't get that chain reaction. And the uranium in nuclear power plants is also has less. They call it fissionable. I think that's the word for it, or fissible, whatever. Less uranium 235, so it's not going to explode. We talked about in class 3 examples of a meltdown throughout history, Chernobyl being the most famous. Um, and despite the bad reputation, nuclear power plants have not led to that many deaths directly. Um, Things like coal and oil have done so much more with the smog, the dumping, and just the whole climate change thing. That they are so much worse for literally like everyone than nuclear power. Nuclear fusion, on the other hand, is the opposite of fission. Instead of breaking apart an atom, you are combining them, two small atoms. This is like fusing them together. This is like Vegeta and Goku. That's literally like, yeah. There, this is fusion. Goku and Vegeta fuse together, and they create something even more powerful. That is them releasing energy. I'm bringing it with the Dragon Ball references this chapter. That's what fusion is. This releases more energy than fission, and for honors class, you should know why. We at the moment cannot use this for electricity. We just don't have the technology. It's been something that, if it did happen, would be fantastic. But who knows? I don't know. It's maybe one of you will solve this issue one day. That would be amazing. Hydrogen bombs are fusion explosions. They use a fission explosion to trigger an even larger fusion explosion. And we talked about the issues of living near one of the largest cities in the world. Um, and we talked about the whole duck and cover, or I think I don't know if I did that in my honors class, but this fear of nuclear annihilation was so driven into the psyche of the Cold War, of adults that are still alive today, that, whether it was true or it was propaganda, that there's so much opposition to nuclear based off of that word because of the connotation of things like Chernobyl, because of the connotation of nuclear annihilation, that this science is just so misunderstood that people just don't understand it. One of my goals for this class is scientific literacy. I don't want you to be scared of a word because it says nuclear. Nuclear bombs are scary, absolutely. But radiation, mm, normal. It happens. There's radiation in bananas. That's my TED talk. Um, Lastly, I'm just gonna say this: you're gonna have a extra credit question that's gonna be asking, what is your opinion on should the U.S. um create more nuclear power plants to combat climate change? I'm saying that right now, and I'll say this in class. I want there to be something to come out of this current day stuff. Um, and as I will say in class, our curriculum, you know, assumes that climate change is real because it is, and that gives me the freedom to talk about this in a public school setting, which I'm very thankful for. Because as young folks, and I'm lumping myself into this um, category, I and you have many years to live on this planet, and if we have if we ruin this planet, what are we gonna do? We're gonna fight each other in the resource wars? No. We combat climate change now. We leave a better place for us and for our future and any future offspring we have. Um, and I think, and I will say, I'm not one to get, I don't want my political beliefs to be explicit. I think that's not my role. And many times when it comes to certain things, there's not really this side and that side both have good arguments, right? Climate change, that's real. There's no, oh, well, what if it doesn't exist? No. That's the type of thing that undebatable. This, however, this topic, the viability of nuclear power in combating climate change, is a legitimate both sides good pros and cons. And I'm saying that as somebody that is very opinionated on certain topics. Um, I truly believe that there's no correct answer to this question, or at least it's not simple. It is very complicated. There are multiple factors, much more than we're even going to discuss in a single class. Um, but keeping on top of current events, this is important. So that's why we're doing this. So that's all for the study guide review. I know this is long, but because I rant, all that stuff. Um, we're going to review this in class. Um, I don't want this to freak out. I know there's a lot. I know this is relatively long, but this is really a giant review of every single thing that I've talked about throughout this entire chapter. Like, my slides give you more pictures, they give you more visuals, so they're more detailed than this, but this is really a comprehensive overview. So that's all for scholars. I'm now going to transition into some of the honors material. So if you are in my scholars chemistry, you can get to doing some of the practice problems I'm going to be posting and studying this. And when I say you are studying this, you should be using good study practices, not just reading the notes or listening to my video. Please make flashcards, write stuff down, teach your teddy bear whatever it is that lets you study better. All right, honors. Let me get back up. Um, all this kind of stuff is the same. You probably have a more difficult question for isotopes and stuff. Um, let me see. All right, here we go. You should know about the upper limit of protons, right? So we talked about the proton-proton repulsion having a longer range than the strong nuclear force. So if we go back to, not Goku, but uranium nucleus. Let's just talk about this. Here, open this on up. So if the orange proton here, I'm going to open up here. Can I just, okay, here we go. This proton here that I am highlighting, it will still, at this distance of the proton, and we're not going to go into specifics about how much that distance is, this proton here still has a repulsion force between this proton, right here. However, the strong nuclear force really only is like the proton or the neutron next to you. So this proton has a repulsion from here, but it doesn't have that same attraction. So when you get to a certain point, this atom is just too big for its own good. It just gets like crushed on its own weight because no matter how many neutrons you add on to it, that balance is just it's just not in it's won't fix itself because of the distance between the two. And this happens with polonium. So, polonium, radioactive. Bismuth, not radioactive. Or at least it is so stable that we can't tell if it is radioactive. So anything on polonium, radioactive. Astatine, radioactive. Radon, all this stuff, not these ones, all these are radioactive. All right. Finally, let me see. You should know how to calculate the mass defect of an atom. This is that missing mass that we spent time on. Um, I would review this. I don't want to make this video too long, but basically what you need to do is you're going to need to, and you should see this as a question in the practice problems, you add up. So you do, let's say there was 12 times the mass of a proton, 12 times the mass of an electron, 12 times the mass of a neutron. You would add up all of this, and that will give you a number. And then you would subtract this number from the mass of, in this case, this would be magnesium 24. So you take the mass of magnesium 24 minus this number, that gives you the mass defect. And that will give you the mass defect in Daltons. Now, you have to take this number. I'm going to use it as MD. That is our mass defect. Convert this from Daltons into kilograms. My practice problems will do this. I will go over how to do this. I will show you on the calculator, but you got to know how to do this because we are going to be doing a lot of calculations that use big, numbers like this or really small numbers, right? This is why I taught all that scientific notation. We're going to need to use it in the next, for the rest of this class, basically. All right, I want to do it now. Making this clear. This is a skill you're going to be using, is using calculations of really, really big, really, really small numbers like this. Convert this into kilograms. And now, E equals mc squared. So you take C, which is 3 times 10 to the 8th meters per second. You're going to square that. C squared equals that. Multiply it by this mass in kilograms, and that will give you your answer in joules. There is a different unit called a electron volt, but we're not dealing with that. I'd rather keep stuff in joules rather than introducing another unit. All right. And because I want you to do these calculations, because I'm just so mean like that. All right, going to this thing here. I think there is. Oh, yes. Honors, calculate this amount. That's the same thing. You go to a nuclear equation. You will take the mass on the left, Subtract the mass on the right. Whatever the mass difference is, you're going to do that same thing. You're going to convert that from mass to energy. So same thing, just different calculation. And there's an example of that in the practice problems, which I'll go through. All right, this thing. You're going to see questions like this. In the practice problems video, I'm going to go over it. N, how much you start with. N naught, how much you started with. So even if you can convert this into percentages, N is how much you have, N naught is how much you started with. Even if you don't know how much you started with, you can still do this as a percentage, right? If you started with, let's say, 8 out of 100, you started with 100 grams, you're now at 8. Well, this is the same calculation as 8%. So you can do calculations, making an imaginary sample of 100 grams, and however much you have is your percentage. So when you see percentages, just know that that is n over n naught. So the percentage equals e to the negative kt, which is why when you're calculating the k constant, that's why you set this equal to 1/2 equals e to the negative k half-life. Which I will go through in the practice problems. Not doing that here. All right. So you're going to need to know how to calculate that K, which I kind of just had. You're going to use that formula to find percentages of a material or an amount of that material. Basically, this is radiometric dating, radiocarbon dating, using that carbon-14. You should know what that is. And actually, I should type that in. That you should also know what radiocarbon dating is and how it works. Might be something small on that. All right. Knowing how that works, what it's used for, I'll probably give you some kind of example of that. Something that's been dated from the past. I hope that I change your minds about archaeology because I think it's cool. All right. The last thing I believe is, why does fusion release more energy than fission? So if we look at the binding energy per nucleon graph here, this is the review. I liked, where was the image that I had? This is where I got it from. I had that image. It was somewhere. Oh, this one. Here we go. That's very useful. So, basically, here's uranium-235. This is where it fractures. This amount of energy is the energy that is released in the fission per nucleon. Right here, it jumps very fast. Right, so this is 40, 30, 20, 10. So right here, we're at about a mass of 10. Right? We start from here. That's a massive, mass of 4 is about right here. This amount of energy from nuclear fusion is larger. The amount of energy between the nucleons, that mass defect, is so much, it just jumps up. Because this energy is larger, that is why fusion reactions release a lot more energy. All right? More binding energy is released as energy. So that binding energy keeps it together, and you need a lot more of it, or a lot less of it, excuse me. So when it gets combined, all that binding energy gets kind of released. The difference in binding energy increases, is what I should say. The amount of binding energy between the small atom, it's not that much, because there's only a few things that need to stick it together, but it rapidly increases. That difference in binding energy gets released. as boom. All right, that is all for me. I know this has been a very long video. I hope you have watched through bits and pieces of it. This should be your starting guide for studying. Listen to what I'm saying, take notes on it. Don't just listen to me. You're going to forget it. We talked about good studying habits, right? Make these note cards. Take notes on what I'm saying here as an addendum to your own personal notes. All right? Try the practice problems. That's why I'm delaying between now and giving those problems out. So I will see you all in class, and good luck.